All right, so just a reminder what we're actually trying to do here. We're trying to come up with a circuit that will recognize the pattern 1101. This circuit will have one input X that will give us inputs in a serial manner. It will have one output Z. It will go to high once we have recognized our sequence. And so far, we came up with a state diagram that describes the behavior of our state machine, and we came up with a transition table. Now, the next step that will bring us closer to actually implementing a circuit is to take these states that we gave them some generic alphabet names and convert them into something we can work with in binary. And this is what's called a state assignment. Now, the question is there only one way to assign binary coding to our states? Is there more than one way? Then how many ways? Or is there infinitely many ways to do it? Well, let's see. What are the possibilities that we have to give to our states? Remember, we had states A, B, C, and D. We want to give them some binary coding. Well, we can use a counting order, which will just be straightforward. A is 0, 0, B is 0, 1, C 1, 0, and D will be 1, 1. That's sort of the straightforward, naive way to do it. Another possible way is to use gray code, in which every successive state will only change in one bit. So we might have something like A 0, 0, B 0, 1, C being 1, 1, and then D being 1, 0. Or, for example, who said we only have to use 2 flip-flops? We need to define 4 states, but maybe for 4 states it's better off to use 4 flip-flops. And then we might code something that looks like A is 1, 0, 0, 0, B 0, 1, 0, 0, in which case only one of those flip-flops is 1 at any particular time. This kind of coding is what we call a one-hot coding. And it is pretty useful. It might be useful for our machine now. Let's check it out. But we don't necessarily need only the minimum number of flip-flops to actually code our states. Yes, if we use 4 flip-flops, it means we can come up with 16 different states, but no one said we need to use all of them. We can use only those 4, and then make sure our machine doesn't actually get to any of the other possible states. And that's easy to do using our combinational logic. Now, we can pick any of these ones. We don't know which one of them will actually give us a better circuit. I will tell you that depending on what coding you do choose, you do end up with different circuit altogether, because the combinational logic that drives the flip-flops will be different. Let's, for example's sake, just to see how we go about moving to the next stage, we'll choose the gray code coding for this particular machine. For now, for no good reason, just because I said so. Next week, we will talk about some rules of thumb that will tell us how to choose good state coding for different machines. So essentially, I will replace all A's with 0, 0, B's with 0, 1, C with 1, 1, D with 1, 0, and I rewrite this table in terms of binary codes. So we will either be in state A, B, C, or D, and then we'll either go to state A or state B, and I'm just copying the table from there to here, state A to state C, and then C will either go to D or stay in state C, or it will go, and D will go to state A or to state B. The outputs are just going to be transformed as they are because they are already in binary. We know how to work with them. The outputs don't actually change. And now we have a table. Again, this is a state transition table, just like this one, but this is given in binary codes, and this is something we can work with. Now, one thing I want to show and emphasize in this table here is that even though we're writing the states as a double-digit or double-bit quantities, what they are really is the Q1 will take those values here, and Q0 will take the values here. So when I talk about things like state, for example, 0, 1, it means that Q1 will be 0, Q0 will be 1. And what I want to make the next states to be is, let's say we want to move here, is that Q1 will become a 1, and then Q0 will become a 1 as well. So this is how to read and interpret the binary state table. Now, to derive the flip-flop input equations and the output equations, then we can realize this is really just a truth table. The inputs to our truth tables are going to be the current state and the input to the machine. The outputs from the truth table will be the next state and the output of the machine to the real world. Now, because what I just said, that each one of those Qs is really just a value of a flip-flop. So this Q here, Q1, and this Q1 will treat the binary bits separately. We can treat each one of them as a function of the current state and the current input. And therefore, we can come up with the corner maps to come up with equations to drive those flip-flops. Now, don't forget, in this case, and this is something I want to emphasize again, we can derive the D inputs directly from this state transition table because we know that the next state will just be whatever the input at the D is. So if we know what we need the next state to be, we know what we want our D functions to be as well. This will not be the case next week when we talk about different kinds of flip-flops, that we will need to come up with the mapping between the input to the flip-flop and what will be the value held by the flip-flop. So for now, everything is still pretty easy. The way I wrote the order of the values for those corner maps, putting X as the column and then Q1 and Q0 at the row, just makes it a bit easier to read the things straight from the state diagram, state table up there. Sometimes when I have more than 3 inputs, I will actually shuffle these things around. We will see it happening in chutes. But it's just very important you do realize what the order of the things are. And again, I've done it this way because you'll see it's very easy to read the values straight into the corner maps. So let's derive the equations for D1, D0, and the output Z. We'll change color. So for D1, the inputs to flip-flop 1, I will need the function to be, well, whatever the values here, and whatever the values are here, for the 2 cases where x equals 0, and for the case where x equals 1. So when x is 0, then Q1, and depending on the input patterns here, will be 0, 0, 1, 0. I'm just reading 0, 0, 1, 0. And notice this time that I did not do what I usually do, especially in tutes, that I jump 0, 0, 1, 0, because the values in here are already given in gray code, which matches the order that I have in the corner map. So it's really important to pay attention to those little details, the order of things that you read to the corner maps. And I did intentionally sort everything out very comfortably so that I can just pretty much straight read them from the table into the corner map. When x equals 1, it will be this row here. And I can just read it from the top down as 0, 1, 1, 0. I can do a similar thing with D0, and I'm looking now at the column for the Q0 when x is 0 and when x is 1. When x is 0, I will just read it down as 0, 0, 0, 0. When x is 1, everything will just be a 1. And we'll derive the equation in a second. Now for the output z, I just read those outputs here for when x is 0 and when x is 1 for all the possible current state combinations, just like I've done before. So when x is 0, then all the z's will be 0 as well. When x is 1, I do have the pattern of zeros and then just 1 at the end. The best grouping, and this is not a lesson about corner maps, so I'll just jump into it straight away. The best groupings that we can probably do are these ones here for D1, this big group here for D0, and there's not much we can do with Z, which will give us the equations of D1 is Q0x or Q0 Q1. So this group here and this group here. D0 will be pretty sweet. It will be just x. And then Z will essentially just be a mean term involving not Q0, Q1, and x. So x, not Q0, and Q1. Now that we have equations, this is really, really close to something we can actually implement. Now, a few things we will need in our circuit. We will need 2 memory elements, so we will need the 2 flip-flops, and again we're working with D flip-flops, where this will be D1 and D0. I will number them that way. What will drive each one of those flip-flops will be the equations. Well, D1 will be driven by this equation. D0 will be connected directly to the input x. And then we're going to have some output Z that will be made of some combinational cloud combined from this. Now because I didn't particularly want to draw a whole circuit now, here's one I prepared earlier. So it's got our 2 D flip-flops, as we said. Here's the combinational logic that will drive D1, and you can verify that the inputs to this combinational logic are coming either from the outputs or the flip-flops or from the external X. We said this one will be connected directly to X. And we have the Z output, which is really just an AND gate, ending a couple of outputs from there, and the X inputs coming from there. One element that's sort of new to this whole thing is this reset signal here. Now, in the very last slide of last week's lecture, we talked about direct reset reset and set signals. In this case, this one will be a direct reset signal, active high direct reset. And this is a way to actually put our machine into its reset, its initial state, when we power it up. We don't usually use this reset signal during the normal operation of the circuit. We will usually turn on the circuit, assert the reset signal once, get usually 0 and 0, reset implies zeros. So 0 and 0 into those flip-flops, and then start our clock that will start driving our circuit according to the machine. Now, a little bit about terminologies with direct signals, and this is something you probably will see in the lab. You will see two possible naming for those signals. You either see a set and reset signals, or you might see them as preset and clear, which sort of imply the same thing. By convention, the set and reset signals are usually synchronous signals that will depend on the clock in the flip-flop, where preset and clear are asynchronous signals. What does that mean? It means that if you see set and reset signals into your flip-flops, they will not actually apply until there's a rising edge of the clock, and only then these will override whatever is in the input. So it's similar to pushing the value that you want instead of the D inputs, but it will only apply in the next rising edge of the clock. Where preset and clear are usually what we call the asynchronous signals, and they will apply straight away as you assert them, regardless of the clock. Now in this case here, I did use the word reset, so this one, just by convention, will be synchronous, so it will depend on the clock, but I could have just as well used the preset signal here to actually have an asynchronous. It's just an example. Okay. Questions so far? So just to recap on what we've done, we actually started, if you remember, from an English description of some sequential circuit. We then figure out what the states are for the circuit. We build a state diagram. From the state diagram, we went to a state table using the generic names for the states, the A, B, C, and D. From there, we've done state assignment or state coding, where we assign binary codes to each one of those states, filled the state table using those codes, derived the equations that will drive our flip-flops and our outputs, and then drew the circuit that will do this. Now you can verify, you can sort of take this circuit and then start stepping back, like we've done at the beginning of this lecture. Now, before I move on, there's something I should probably mention. As I said, a lot of students find it really hard dealing with state machines, especially designing new state machines. So in this case, I threw some problem at you, some sequence recognizer. For some reason, the examples are always about sequence recognizers, because they're just very easy to show as examples. But it's not always the case. You might get some problem that you will not actually know even where to start implement this state machine. First thing, don't panic. All right? A lot of people do panic when they see a state machine. They don't know where to start. Start with a circle and put an A right there. Call it your initial state. And then start to think, all right, what's going to happen for my initial state? What are the possible inputs? What do they imply towards the operation of my machine? And it really depends on what your machine needs to do. Now, one thing that worries a lot of students when they design it, they say, oh, I really want to get the minimum number of states, so I really have to think it through. to know what all the different states are going to be at the end, so I don't just go wild and every time I don't know what to do, I'll create a new state and I'll just use that. The answer to that is please do. Create as many states as you need, that as long as you know the machine works, that will actually implement the machine. And the reason for this is that next week we will actually learn how to take an unoptimized machine that has many states and then reduce it to an optimal machine that uses a minimal number of states. So when you start duplicating states, you might not realize that you already have a state in the machine that does what you want, and that's when you open a new state. This algorithm that I'll teach you next week will actually recognize those repeating states and will throw them out of your state machine, and you will end up with an optimized machine. Again, it depends on what your circuit needs to do or what the specifications do. I've only shown you one example of a sequence recognizer, and you know, it's if you get a sequence recognizer, usually pretty easy to go through because you know what the sequence is. But here's a little bit of a complication that I can throw at you straight away. What if I tell you to build a machine that detects one of two different sequences? Then all of a sudden, you, at the same time, right? So you will raise a 1 when this sequence happened or the other sequence happens. And they might not even be similar to each other. So you have to start thinking, okay, so how do I detect both of them? What states mean that I've seen part of this sequence, but maybe I've seen it in this sequence as well? And then things start getting a little bit messy. Again, don't panic. Just write as many states as you need. Maybe even split it into, in this particular case, of two sequence recognizers, or two sequences, split it into two machines, and then later you will unite them together. And you will end up with a complete machine there. The tutorial for next week has quite a few different problems, and they're not always so straightforward. Some of them you will just sit there and try to figure out how to do it. I encourage you to do so, though. I encourage you to sit there and think about the problems and start from somewhere, and you will see that it's not as scary if you try it. Usually a lot of people look at the question, not quite sure how to go about doing this, then look at the solution and say, oh yeah, that makes sense, I know how to do it now. And then when they come to exam or to actually do things, they're like, oh, I don't know where to go from here. So please don't just look at the solution and say, all right, I know how to do it, because chances are you won't. Try to tackle those problems. Okay. That's about that. Any questions so far? Don't forget to write English descriptions to your states, yeah? Because this is the number one rule. English descriptions to the states. So when you call them A, B, C, and D, tell them what they need, what they mean. All right. So what I mentioned before with the one-hot coding, I said we don't always need to use all the possible states that we might have. Take this example here. We might have a 3-bits machine, but we really only need 5 different states. Now, because we need 5 different states, then we can't get away with only 2 memory elements. We will need 3 of them, but we don't need all 8. So there's few states, 0, 0, 0, 1, 1, 0, and 1, 1, 1, that are not actually playing part in this machine. As you can see, none of these states try to transit to any of those unused states. They all stay within their own states there. So when you need to then come up with a machine for this one, and we said this is essentially a truth table. In this case, it will be a truth table with 4 variables, because it will have the current states and 1 bit for input. Then how do we go about actually implementing this machine here? Well, there's 2 approaches. One approach will say, well, I know that these states here will never be used. My machine will never actually get to them. I don't care what the next state is going to be from these states, because I'm sure my machine will never ever get there. then if by using don't cares, I can actually make my implementation a little bit nicer, a bit less messier, let me use don't cares and then implement that machine where, as we said when we work with don't cares, these will go to some certain state, but depending on how we actually draw our truth tables, our corner maps, then these may or may not go to one of the actual used states, or they might actually go between the unused states. But we don't care because we'll never get there anyway. So, for example, by the way, these are not labeled. That's D2, D1, and D0. And as you can see, I've done you a favor, and I'm not filling up the K-maps anymore. But I will try to group them together. Trying to group these, and if someone can see a better grouping than what I'm seeing now, please do tell me. I can probably group these, and I am utilizing the don't care. These ones? Huh? Anything better than this? Yeah. With this one, well, there's not much I can do. Whoa, bless you. And then this one, yeah, I can either wrap it around or sideways. Either way, it's the same complexity. So two options for that one. I just picked one of them. For D0, there's, oh, that's a nice one. Just this one. And I do want to show you the equations because I'm going to make a point in a second. So why did that just happen? Anybody who works with PowerPoint 2010 already? Such a headache. Anyway, for one thing, by the way, it doesn't retain my pen color when I go through the slides. I actually had to patch it to actually get my pen to work. But you don't care about this. I told you I had a fight with my laptop last night. I won, by the way, as you can see. So D2 will be, let's see, so not Q0, not Q1, that's the top here, or XQ2, which is this one, or this one here, which is XQ1. D1 will be X, not Q2, not Q1, or not X, sorry, what? Not X, Q1, not Q0. And D0 will have a nice one, which will just be not X. Now, stare a little bit at how complex these equations are. They are quite complex, even though we utilized the don't cares. And again, this was one approach to what we do with unused states. And this is what we ended up with, and obviously you can implement it. The other approach we might take when we have unused states is to say, well, any state that's unused, I will make sure that on the next clock cycle, it will go to a state that is used in the circuit. And usually we'll take it to some valid initial state. If I define my initial state to be 0, 0, 1, I want any case where my machine somehow magically ended up in one of those unused states, then to transit it straight away into my initial state, so at least I know it stabilizes on the next clock cycle. Now, I'll take this approach if I cannot guarantee my machine to not ever enter these states here. In the don't care approach, this one's here, I can say, well, I can guarantee and I know for sure there's no way my machine will ever go to these states, therefore I don't care what's going to be the next state. Maybe once we implemented these equations, this 1, 1, 1 will just say next state is again 1, 1, 1, and then we'll end up in an endless loop if if this thing actually entered the 111 state. In the second approach, this cannot happen. If we somehow magically end up in 111, the next cycle will throw it back into some valid state, and then the transitions between all the valid states will make sure we never actually get out again to any of the unused states. However, for this sort of safety, there's a price, and this price will be in how complex our circuit will be. And now I've filled up those corner maps there, and we can try and group these together. And wow, this is really bad. I still have my big group here. I've got this one can probably group with this one, and this will be a 4. Now, if you look at the equation that I got here, and you compare with what I possibly can get out of this one, and not to bore you all to death, I won't start to actually derive them, but you can actually see already just on the corner map that we will get more complex equations to the circuit. Let's have a look, for example, at the D1. Each one of those squares will end up in a 4 variables mean term, where in the case here, we actually ended up with something that's smaller than that, with only 3 variables in each one of them. So there's a bit of a trade-off between using whether you don't care about the next states of the unused states, or whether you want to send them to some initial state. I think this slide pretty much says most of what I said before. The second approach is a safer design. If for some reason it does go into those unused states, it will be sent back to the initial state. But if you do use don't cares, it will give you a simpler design. Now the next question that I usually always get is, so which approach should we use? Well, depending on what your project is and what your and how critical it is, and how sure you are not to enter those unused states. If you have some reset signal at the beginning that will force it into your to its initial state, and there's no transitions from there to the unused states. And remember, state machines don't just jump into something that they weren't supposed to. Once you're in a used state and you do jump around between the states, it will be nicely behaved. There's no way a state machine will sort of say, okay, I had enough of this, I'm going to one of the unused states. But usually we might get into unused state if we start up the circuit and we don't take care to actually reset the values into the flip-flops using, say, a synchronous, either a synchronous or an asynchronous direct signals. So again, depending on what you're working with. All right. Any questions so far about this? Okay.